ME495 is the Mechanical and Thermal Systems Lab. This lab is held in EIS 12 and in the A-Lot. ME495 provides students with experience in designing, performing, and reporting results for experiments on mechanical and thermal systems, mechanisms, vibrations, structures, thermodynamics, and heat transfer. This lab covers concepts such as data acquisition theory, instrumentation, sensors, data reduction, statistical and uncertainty analysis, and design of experiments. ME495 experiments include a hydrostatic pressure lab, a tube heat exchanger lab, a plate heat exchanger lab, BoMKM lab, a laser vibrometry lab, a vibration analysis lab, a refrigeration systems lab, a Brayton Cycle lab, and a Rankin Cycle lab. Students determine the hydrostatic thrust acting on a plate surface immersed in water when the surface is partially submerged or fully submerged. The position of the line of action of the thrust is determined experimentally and compared with the theoretical position. The Tubular Heat Exchanger experiments allow students to learn about different types of transducers used to detect and measure the physical properties when calculating the heat transfer between the hot and cold media. A HT30XC heat exchanger unit and the HT31 tubular heat exchanger are used in this lab. Students utilize this collected data to determine the heat transfer coefficient and the performance of the heat exchanger. The theory of the tubular heat exchanger is then applied to the plate heat exchanger experiment. An HT30XC heat exchanger unit and the HT32 plate heat exchanger are used in this lab. Students utilize collected transducer data to determine the heat transfer coefficient and performance of the heat exchanger. The BoMKM experiment allows students to determine the heating value of a solid and liquid sample. As the fuel sample is burned, the heat is transferred to a known mass of water. A precision thermometer and thermocouple are lowered into the water to measure the change in temperature. To ensure the temperature is homogeneous, a paddle mixes the water during the experiment. The temperature change is then used to determine the energy released during the fuel combustion. In this lab, Polytech PDV100 laser Doppler vibrometer is used to measure the displacement, velocity, and acceleration of the mechanical vibrations of a speaker cone when harmonically excited at various frequencies. The measurements are then analyzed to determine the dampening ratio of the speaker cone and the mechanical limits of the system. This lab employs a Model 95 ME5AI vibration analysis learning system to teach students how to use vibration analysis to inform equipment maintenance. Students learn industry-relevant skills, including how to use a vibration meter to take measurements, how and where to take measurements on various types of power transmission systems, how to analyze the results, and methods to minimize vibrations. Students learn how to monitor the condition of a belt drive and correct problems before they cause system failure. Vertical and horizontal readings are made to detect worn or stretched belts, and axial readings are used to detect belts or sheave misalignments. The arm-filled RA1 refrigeration unit is used to demonstrate the important features and operation of a vapor compressed refrigeration system. Students analyze the combined process of compression, condensation, expansion, and evaporation during the experiment. The expansion valve is varied to control the liquid flow for different loading conditions, and parameters such as temperature and pressure are recorded to determine the system performance. The results are logged by students, and they compare multiple graphs to identify the optimal settings. The Brayton Cycle experiment utilizes a gas turbine power cycle to demonstrate the cold air standard assumption model. The portable propulsion laboratory containing a model CM14 axial flow gas turbine is used in this experiment. Students apply theoretical equations for Brayton cycle analysis using empirical data collected during measurements. Before the lab is conducted, a safety briefing is performed to ensure observers keep a safe distance and wear appropriate ear protection at all times. The Rankin Cycle Heat Engine Laboratory utilizes a working model of a steam power plant. The students learn how to select the appropriate transducer to measure physical properties necessary for calculating the efficiency of the Rankin cycle. The cycle is also analyzed with empirical measurements at different paths in the Rankin cycle.